PhD student at Université Grenoble-Alpes in Grenoble in France. And so this work that I'm presenting today is one of my work, which I presented 2 weeks ago at ICLR. I don't know if any of you were there, but there were a few people with who we discussed the paper in general. So the beginning of the slide is probably very probably not the most useful for everyone, but the general idea is why do we want to explain AI systems in the first place? And there's a lot of different practical reasons, moral reasons, legal reasons, technical ones, and social ones. Some of the important ones are, for example, in terms of legal reasons, there might be legal compliance, who might be required to have explainable systems in some legal frameworks. And of course, it's also useful for things such as education. It's easier to explain and teach AI systems if they're explainable, things like that. So all the classical ones, but in addition, I would argue that there's a kind of more general and philosophical reason, which is the idea of explaining complex systems. And what do I mean by complex systems? They're just simply those systems that exist in all kinds of fields of science. For example, in climatology, the atmosphere is a complex system. The human brain can be seen also as a complex system, the immune system, language. And so one of the primary goals of science is just to explain those systems in general. And I would argue that actually AI systems, they are the kind of the easiest complex systems to study, because one of the very nice things about AI systems is that we can have full and perfect observations. We know exactly what the architecture looks like, and we can have insights on the computations that are happening at any moment. In addition to that, we know that now there's a high diversity of different AI architectures, and those models are fully manipulable and controllable, which is not the case with things like the atmosphere or the human brain. So I think the AI systems are really a perfect setup for interpretability in general. And of course, I imagine most of you know about mechanistic interpretability. And here, the definition that I'm using, I'm really viewing mechanistic interpretability in a particular perspective, which is really the idea that we want to extract algorithms from neural network. So not just only features, but really a complex algorithm that should be simple and human interpretable, and that we imagine are embedded in the neural network structure. And so we know that, of course, we've found before that there are nodes in neural networks that compute features that seem to be interpretable. And that when we connect those features together, we obtain circuits which seem to have some explanatory power. We know that this has been done for LLMs as well. So a lot of examples that I'm sure you're all familiar with, and for specific tasks as well. And here in the framework that I'm going to be talking about today, I will say that an explanation in Mech Interp has two main components. There is what we'll be calling the what, and the what is essentially the high-level algorithm that should be approximating the model's behavior and tracking its internal computation. So the what is the algorithm, and the second component is the where, and the where specifies exactly where and how this algorithm will be embedded in the computation of the model, so in the model's activation, typically. And when we put these together, we obtain an explanation, and I also call those explanations computational abstractions. Why abstraction? Because if we're going to be working with a subset of a neural network's computation, so it is a kind of abstraction, and it abstracts those neural activations into some high-level features. So this is why I'm going with the term of abstraction. So this is a typical example here where we're going to have a basic neural network, which is represented here by its computational graph. And then we have a circuit, and the circuit is going to be a subset of a neural network or a subgraph of this computational graph that computes, that is responsible for a particular task. And then the computational abstraction is this circuit plus a mapping that explains for each of the neural activation what features they correspond to, and for which values they do so. And of course, one of the question is this realistic? And well, the two main assumptions of Mech Interp are that the what exists and that the where exists. So what do we mean by the fact that the what exists? Well, that means that the neural network's behavior must be explained by an algorithm that is simpler than the full network's computed function, because we can always explain a neural network by its entire function, but the idea is that there's something simpler that can also be used to explain it. And the where exists, so here what we mean by that is that the algorithm must be executed by a circuit, which is a subset of a network that should ideally be sparse, because again, if we want to use the entire network, it's not really an abstraction and it's not useful for explaining. And we know that there are experiments in literature that show that those assumptions are not completely baseless, and that neural networks are usually over-parameterized, and that we can usually approximate the full network's performance with only a subset of the network itself. And so what we did in our work is the first thing we did is identify two categories of approaches that are used in Mech Interp for extracting explanations. And those approaches are simply the where then what and the what then where. So let me just go a little bit in detail about that. So the idea of the where then what is that we first extract a circuit, and the circuit again is going to be replicating the behavior that we're interested in. And then once we have a circuit, we interpret its components and try to uncover the high-level algorithm, so the what. So here in this diagram, it's really done from left to right. We start by localizing the circuit, and then we interpret that circuit in terms of algorithms. And here what I'm interested in is what metrics do we use to validate explanations that we find. For the first step, for extracting the circuit, one of the most common metrics is what we call circuit error. And circuit error, we essentially just check that the circuit replicates the full network's behavior. So we run our full network on a set of inputs. We also run our subset, so our circuit, on a set of inputs, and we check whether they agree or not. And we get a metric between 0 and 1. Once we have the circuit and we want to, and we have the second part, so the mapping from the circuit to high-level features, the second metric that we often use to validate those are what we call mapping consistency here. And what we do is that we essentially check that the computation are aligned both in the neural network and in the high-level algorithm that we propose. And this is what I show here with this diagram at the bottom. So essentially we have two parts. We have our network, which is what I call the low-level system, and the high-level explanation. So the algorithm that we hypothesize is in the neural network. And if I go with some activation of a neural network and then I propagate those activations further into their children activations, so we obtain different values. But then the idea is that we have a mapping that tells us that those activations, they correspond to some high-level features. And if I have my high-level algorithm and I also use those high-level features in the algorithm, I should also get some children values. And the idea of this diagram is that it doesn't really depend at which point we apply this mapping from the low level to the high level. It should align consistently. So no matter which path we take, whether we take the purple path here or the red path, we should arrive at the same output. And this is what we mean by mapping consistency. Essentially, that the computations are aligned on both levels, no matter at which moment we go from the low level to the high level. In practice, how do we find circuit? There's a very recent work that was also presented at iClear 2 weeks ago that showed that, among other things, enumerating all possible circuits in a neural network is not really doable because it is short p-complete, which we know is at least as hard as NP-complete. And so it's not tractable in most cases. The enumeration is just too high to be computationally feasible. And one of the methods that are often used to find circuit is causal mediation analysis, which what we do here is essentially we try to find the subset of a network that is going to carry the information from the input to the output. And then we use causal mediation formulas to check for each individual component of the network if it should be included or not in our explanation. For the second part, once we have a circuit and we try to interpret it and find the algorithm, typically in the literature it's often done with a mix of data analysis and human input. One of the heuristics that is often used is activation maximization. So we look at a particular neuron or component and we try to find in the input space which inputs maximizes the activation of a component. And that can give us some hints as to the function of that component, just by looking at which inputs trigger it the most. So that is the first approach. Then the second approach is the reverse one, which we call the what then where. And here we first start by hypothesizing a candidate high-level algorithm, so the what, and then we search for a mapping, so a where, between the states of that algorithm and the subspaces of the neural activation of our model. And here the metric that is used, well, essentially what do we want when we have a candidate algorithm and mapping? We want the high-level and the low-level states to be causally aligned in the sense that they respond similarly under interventions. And for that, there is one metric that has been proposed by Geiger in 2022, which is called intervention-interchange accuracy. Let me present that metric very quickly. So let's say we have a neural network that adds 4 numbers. The neural network is depicted here on the right, so a very simple MLP here. And our hypothesis is that it uses this algorithm on the left. So it adds first the 2 left numbers, then it adds the 2 right numbers, and then it adds all of these together. And let's say that in our working hypothesis, we also assume that this intermediate state, the A plus B, is stored in those 3 neural activations on the right, and that the other intermediate variable is stored in this purple activation on the right. And now we want to validate whether that's true or not. And what is used by this intervention-interchange accuracy is essentially we're going to run our high-level algorithm and our low-level neural network on 2 random samples of inputs. So we have our inputs here, 6, 2, minus 4, minus 5, and here 3, minus 1, 4, 2. And we just run both the high-level and the low-level algorithm on it. And then we're going to perform a counterfactual intervention. So we're going to look at one of the intermediate variables randomly. So for example, here, this intermediate variable on the right. And we assumed earlier that this variable corresponded to the 2 neural activations on the right. And now what we're going to do is that essentially we're going to rerun both models on one of the inputs, but we're going to perform an intervention. So we're going to look at this variable that we selected, and we're going to replace its value with a value that it had in the second sample. And since we know that this variable, we expect it to be aligned with those activations here, we're going to perform the same thing here. So here we override the activations, those 2 activations with the values that they had for the second sample. And then we let the rest of the computation propagate until we get the output. And the idea is that if the model really agrees with our high-level description, then we should obtain the same output. And this should be true if we do it for all possible inputs, all possible intermediate variables, and all possible interventions. And so in this case, we will say that the models are causally aligned if their output is the same for all possible interventions. And this is the metric that we call IIA, or intervention-interchange accuracy. And it's also a value between 0 and 1. And in practice, of course, we cannot test all possible inputs for a neural network, so usually it is approximated with sampling. And now with this approach here, so to use this method, we need to have an hypothesis of a candidate algorithm and a candidate mapping. To find candidate algorithms, there's no automatic method so far in the literature, as far as I'm aware, and it's typically done through simply human input. We just say, right, our model is performing this task, here are some ways it could be doing it. And to find mapping, same thing. It's not computationally feasible to do an exhaustive search of all the ways the algorithm could be aligned with a neural network. But for example, there is one method called distributed alignment search that uses gradient descent in order to find alignment. Right, so if I summarize this whole part, which was really just the related work, but that is really important for the rest of the presentation, we have those 2 approaches, what then where, and where then what. And for each of them, we have different heuristics or different search method, but most importantly, we have different metrics that allow us to validate our explanation. And now here's the actual question that I had in my paper. So the current method that we use to find circuits, to find explanation, they're not exhaustive because they cannot be exhaustive. But what we see is that we're usually able to find explanations rather easily. And the question is, if we could actually exhaustively check all the possible explanations, could we guarantee that there is at most one valid, one correct explanation for a given model? And this is basically the idea of unicity, or in statistics, it also corresponds to the idea of identifiability.
And so is this really an assumption that people make? Well, if we look in the MI research in general, people never say that their method will only find one explanation, but it's kind of an underlying assumption that everybody makes. So here we have a list of various papers that talk about mechanistic interpretability research, and people always say we're looking for the circuit. We're uncovering the circuit that is responsible for this task, the circuit for agreement, etc. So even if it's not really something that people clearly voice, there seems to be this assumption that there is only one valid explanation. And this makes sense if you consider human cognition and psychological tendencies, which have shown essentially that the brain is always looking to unify information, even if they're coming from disparate observation, and find one unified narrative, and essentially getting cohesive patterns. And also the idea that there's a psychological need for cognitive closure. And so the idea that we could potentially have multiple valid explanations that would be incompatible, it doesn't sit right. It kind of disrupts coherence, and we have this idea that we might not really understand what is going on if that was the case. Which says, well, the world is an extremely complex thing, and we cannot just fully describe it by a single explanation. And the idea behind explanatory pluralism also says that it can be all right to have multiple explanations, but they need to either address different explanatory goals. So, for example, if we have different goals of a different behaviors of a neural network, it's normal that we get different explanations. Or if different explanations differ only in level of abstraction. So, if we zoom in or zoom out, we get different explanations. In that case, that is also normal. And the idea of this paper is that we're going to look for conflicting explanations by having a fixed goal and a fixed abstraction level. So in that case, we shouldn't have multiple explanations. And what do we mean by explanations that are conflicting or incompatible? Well, we say that two explanations conflict if they either posit that the same behavior has two underlying algorithms that are different, or the same algorithms but in different places. So now what is the experimental setup? So really here we're trying to validate whether it's possible to find multiple explanations for a neural network's behavior or not. And we're really only looking for counterexamples, simple identifiability counterexample. And for that, it's enough to work with extremely small neural networks, or MLPs, which are basically toy models. And what we do is that we're going to train our MLPs on the ZOR function, which is kind of also the basis of a lot of research work. And we know that the ZOR function requires at least 2 layers to be implemented. So now let's say we have a MLP that is trained on the ZOR function. What does mechanistic interpretability look like if we're trying to apply it to that small model? Well, essentially, we're looking to find how this logic gate ZOR is implemented. And so the what algorithm would simply be here, which combination of logic gates transform the input into one output. And the where here is simply where would be each of the intermediate logic gate implemented in the MLP. So what we do here is that the nice thing is that we don't apply any specific method of mechanistic interpretability. Since we work with extremely small model, we're actually capable of enumerating exhaustively all possible circuits and interpretations. So for the first approach, the where then what we do is that we enumerate all possible circuits, all possible subgraphs of a computational graph. And if you remember that the metric that was used for circuit search was circuit error, here we simply keep all the circuits that are perfect and simply have 0 circuit error and perfectly replicate the full model's behavior. And for the interpretation search, once we have a circuit, how do we interpret it as a combination of logic gates? We apply some kind of recursive search. I can go into detail later, but it's not the important part here. And essentially, we just ground the different neurons we find and ground them as logic gates that are grounded into the activations of a neural network. For the second approach, so the what then where, this one required having an hypothesis of an algorithm and a mapping. And what we do is for the algorithms, well, an algorithm again is a sequence of logic gate that is equivalent to XOR. And what we do is we simply enumerate all logic formulas are equivalent to XOR, and logic formulas can be seen as a tree of logic gates, but it's just taking the parsing formula of the parsing tree, of the formula itself. And then when we have an algorithm, well, here again, we enumerate all the possible mapping between a particular logic formula and the neural network. And here we use, again, the metric of IIA, so intervention accuracy, and we only keep the ones that have 1 for all variables. So we're really looking for interpretations that maximize all the criteria that are typically used in mechanistic interpretability. And so here is a very simple visualization of the neural network we use. So it has 2 inputs, 1 output, and 2 layers with exactly 3 neurons. So it's hard to get any smaller than that. And this neural network is trained to implement the XOR gate. And what we do is, first of all, when we do the circuit search, we find 52 circuits that replicate the initial behavior fully with 100% accuracy, so 0 circuit error. And then if I look at one of those circuits randomly, I can see that there are multiple combinations of logic gates that are grounded in the neural network's activation and are equivalent to a XOR gate. So we're not finding a unique algorithm, and we're not finding a unique location. For the second type of approach, the one where we start from formulas, we find that there are 10 different formulas equivalent to XOR that can be found in the neural network. And if I pick one random such formula, I can find 4 different places in the network where it's implemented as well. When we add all of those results together, we find that with a where then what approach, we find 52 perfect circuits, and in total 48,000 consistent interpretations. And in the other way, when we do first the what and then the where, we find 10 different formulas, 10 different algorithms, and in total 40 mappings that maximize the IA metric. So essentially what we have is that we have an identifiability failure at every stage. So no matter which method we use, we're not finding a unique where, and we're not finding a unique what either. Because here, if we look at this, in total, we find 48,000 explanations for simple XOR. And according to the metrics that we typically use in Mech Interp, all of those explanations are valid. And there's no obvious way to choose one over the others. Then what we did is that we did a bit of quantitative analysis or further experiments to see how that would vary. So we repeated exactly the same experiment with various seeds, and we changed the target logic gate. We also tried to make the neural network a little bit bigger or a little bit smaller. We also tried training our neural network on multiple tasks at once to see if there was some kind of over-parameterization thing going on, and also the training dynamics by making the model converge more or less, running for longer, shorter, and changing the training distribution. And what we see here, so here K is the number of neurons on every layer. So the basic setup that I showed earlier was with K equals 3. But when we increase the size of a neural network, it gets even worse. So the number of explanations we find gets 10 times, 100 times bigger. So the blue graph here, the blue box corresponds to the what then where method, and the other one is the where then what. And you can see that even here, in the case of K equals 5, we have a neural network that has 10 neurons, and we're finding over 1 million valid explanations for that neural network. When we train the network on multiple gates at once, it doesn't really get better either. In fact, it keeps getting worse. In addition, we also saw that training the model for longer or less doesn't really change anything significantly in terms of results. Neither does skewing the training distribution. We also showed in the paper that, of course, these are extremely small models, but at least in the case of circuits, the problem does not disappear at a larger scale. We showed that if we train an MLP on the NIST dataset, then we also have a minimum of 3,000 circuits, and very much a lower bound compared to the true value. Worse than that, if we take untrained, so random neural networks that just happen to kind of randomly implement the logic gate, we still find multiple incompatible explanations of in those neural networks. And we also saw that if we relax the constraint that we have on the inputs and outputs, we find that basically most neural networks have somewhere in their graph all logic gates. And this is really problematic because it means that if you just stack a bunch of neural networks on top of each other, you can potentially find any algorithms because logic gates are a complete model of computation. So, so this is a big problem. So let's think a little bit about what went wrong. And first of all, the question is, does it really matter to want to find a single unique explanation for a different for a given behavior? And I would say that this really depends on why we're trying to explain the neural network in the first place. If we're just trying to have a neural network that is predictable, or that we can control, then it might be okay to have several explanations. We just need to pick one that works for what we're trying to do. But I would argue that it's still kind of problematic in the way that it doesn't really instill a sense of understanding. We still don't feel like we understand what's going on in the network if we have 50,000 explanations that are all the same. And so how could we potentially resolve this issue? If we do decide that it's important to have identifiable explanations, then what is clear is that the current criteria, so the current metrics that we use to validate explanations, they are insufficient. And we could think, okay, how could we improve on those? A simple idea would be to add more heuristics. So for example, let's take, when we have 50,000 explanations, let's take the sparsest circuit that we find. It's, first of all, I think it's unlikely to solve a problem in general. Also, if we imagine that we have a much bigger neural network, does it really make sense to pick one explanation instead of another because one has 935 nodes and the other has 936? It seems a little bit weird. And also in our experiment, it simply doesn't suffice. If we just use simplicity, if we try to find the smallest circuit, the smallest explanation, it still doesn't converge to one explanation. We still get multiple dozens, hundreds, thousands. The other idea would be that to reinforce metrics that are used in mechanistic interpretability, using the ideas of causal abstraction. What is causal abstraction? Well, first of all, it stems from the idea that we should use causality to validate explanations. And why are we looking for causal explanation? Because simply put, by definition, causes explain their effects. Causal abstraction, or causality in general, it's a conceptual framework that's exactly used for the kind of thing that we're looking for here, which is used to understand and simplify complex systems. And it also focuses on key cause and effect relationships, but the main difference compared to what a lot of the methods currently are doing is that while causality also looks for high-level variables, it makes sure that their connections are causal. And one of the main tools it uses for that are counterfactual interventions. And so this is also a tool that is used to predict the system behavior by working with a simplified model, but it ensures that the model we use is causally accurate. And there's this idea of ladder of causation that is used a lot in causality. And the idea is that causality, it's not a simple binary thing, but there's kind of levels to it. And the first level would be association. When we check if there are correlation between things, it's a very, very mild form of causality. Then a bit of a stronger element is when we do intervention. So we actually modify the value of something and we see well, whether the results agree with our simplified model or not. And the highest level, the one that's really needed to call something causal, is counterfactual. So we really replace a value, we force it to have a value that it couldn't have in reality, or that is not typically observed. And if we look a little bit at the current methods or some of the methods that are used for circuit discovery, for example, when we look at activation maximization, which is, again, we're looking at one component and looking at which input maximize it to see whether that component is useful or not, we're just looking at correlation. There's nothing causal about it. So it's basically the rank 1 of causality. But there are more recent methods such as causal tracing or causal mutation analysis. And as the name implies, those are causal methods. So they're actually doing a pretty good job of checking for causal explanations. However, if we look at the metrics that we use to validate explanation, circuit error, we just check that our circuit and our and our low-level neural network agree on all inputs. So we just check for correlation. It's a rank 1 method, so it's not a causally strong method. The mapping consistency, that second metric that I also showed, depending on how it's implemented, could be under rank 1 or 2, but it's also not a causal method. What about IIA, the method that I showed that actually use counterfactual interventions? Well, if we just look a little bit at the result that we found earlier, using the what then where method, we find much fewer explanations. We only find a few dozens of these compared to dozens of thousands. And actually, this idea of intervention interchange, it is in fact directly inspired by causal abstraction. As I said earlier, we actually replace values, we perform counterfactual interventions. However, the way IIA is currently implemented does not fully implement causal abstraction, and I think this is why we're still finding multiple valid explanations. Why? Well, in the framework of causal abstraction, we require that all the possible low-level states of the model should be included somewhere in the high-level representations. So we need to make sure that every single neuron of our network is included somewhere in the explanation. It also requires that we need to explicitly state what values of each neuron correspond to which high-level feature, which is not something that is currently checked by IIA. And the last thing is that if we have an explanation that ignores some part of our network, then we need to be able to justify causally that those neurons actually don't do anything. So here, for example, I don't know, let me get an example a bit earlier. If I have a circuit like this where I just say, well, these neurons in green and pink are the ones that are used, then I need to prove that those neurons in gray are not doing anything and are not doing anything for the computation. And IIA in its current form doesn't check for that. However, there are more recent works that have been trying to introduce the concept of faithfulness in mechanistic integrability. So there is a paper that is called Have Faith in Faithfulness, where not only we check that the circuit replicates what the full model does, but we also check that what is not in the circuit doesn't have an impact. So we try to evaluate the impact of excluded elements. So that is a step in the right direction. So what is the conclusion of this work? Well, I think the current metrics for validating MI interpretations can definitely be improved. There's definitely room for improvement, but now let's assume for a second that we have a perfect metric, so something kind of in the style of IIA, but that's actually fully grounded in causal abstraction. And let's say that we use that to validate our explanations. Well, there's three possible cases. Either when we analyze one model and one behavior, we only find one explanation that has the maximum score. And that would be perfect. That would basically solve all of our issues. And if we can prove that somehow we only have one explanation that is valid and the best one, I mean, that's what we would like to have. But I don't think it's very likely. The second thing that may happen is that when we do that, we don't find a single explanation that maximizes all the criteria. So there are some explanations that are good, but nothing that is perfect. If that happens, and I think that's very likely to be the case, then what that might simply mean is that the assumption that we do in mechanistic integrability that a behavior can always be explained by a some kind of sparse algorithm in a sparse subset of the network might just be unrealistic, and that there is no way of explaining a model other than using the complete computational graph itself. It would be a little unsatisfying, but I think it's a possibility. And the last case is, what if we have a perfect metric and we still somehow find multiple incompatible explanations? What does that mean for us? Well, there are domains of sciences where we do have competing theories that coexist, even if they are incompatible in some sense. For example, in the field of physics, and especially classical mechanics, we have two different formulations, the Lagrangian one and the Hamiltonian ones. And those formulations, they cannot be distinguished through experiments. They produce exactly the same experimental prediction, so there is no experiment we can do that would tell us, well, this one is right and this one is wrong. But those two formulations, they kind of are incompatible in the sense that they assume that the underlying entities are very different. So this might be the case for mechanistic integrability, which would be really interesting. And this all kind of ties with the idea of contrastive underdetermination, and this philosophical debate about, is it possible and is it really something that we want to be able to actually determine unique scientific explanations for empirical evidence. So if that's the case for mechanistic integrability, that would be a very interesting result, but of course it's not something we can show yet at the moment. So thank you very much. If there are any questions, I have a lot of time and I will be happy to answer.
There is some questions that happened while you were talking on the reading group chat.
Oh, sorry, I didn't see. Yeah, I see that. Can you extend about the 48,000 explanation because network? Yes, but the thing is, an explanation Yes, so here, like I said earlier, I have a neural network that has only 6 hidden neurons, and I'm still finding 48,000 explanations because, first of all, I'm looking for circuits that replicate the model's behavior, and I find 52 circuits. There are subgraphs, so there can be more subgraphs than units in the neural network. And then for each of those subgraphs, we interpret it in terms of combination of logic gates, and we find multiple, on average, almost 1,000 different combination of logic gates that are grounded in the network's activation, and that are equivalent to the target logic gate of Zor here. And so when we do that, we do find more activation, even in a very small network. You do end up finding thousands of different explanations.
There's also some others on the reading group channel, on the text channel.
The Eichler paper that showed that circuit enumeration is sharply complete, that is, it is called something, a framework for inner interpretability. I do have the references at the end. Let me just check real quick. Yes, that's the first one here. The computational complexity of circuit discovery for inner interpretability by Adolfi and Vilas, which were also at Eichler 2 weeks ago. One comment, the output of a net is a weighted sum over a large ensemble of circuit. The question should be, how does the output of a network select a circuit, or how does the sum over all the circuit give the answer? Yeah, I actually agree. I do think my intuition is that there are no ways to explain a neural network other than using the full computation itself, because it's very unlikely. I mean, for specific behaviors, of course, there's going to be large parts of a network that are probably going to be inactive, but I think it's very likely that there are different circuits or different circuits that are used for different things. And I mean, exactly how you say, there is some kind of weighted sum, and the interesting part would be, how is this selection, or how is this weighted sum done? So we're noting that the input output Jacobian encodes this sum. Okay, interesting. Do you have any work that was looking into that, or I would be interested in reading that. Questions. Coming back to the other circuits questions in the meantime. Since neural network circuits implement algorithms using vectors and not symbolically, can we not have multiple circuits implementing the same algorithm for different data slices? I am not sure I understand the question. You're trying to say that basically we should have...
Yeah.
Okay,
So I mean,
Mhm.
I might be wrong here, but my intuition here would be that, like you're implementing like a circuit is implementing like a computation, right? And
Yeah.
but like it's not like we have actual variables. Like there might be limits of, I mean, of like, so for different input data slices, you might just learn like different sets of weights which implement the same algorithm. It might just be easier to do that rather than having it all compressed in a single circuit.
Yeah, that's also something that is likely, but I think in that case, again, when we propose an explanation, we shouldn't just say, well, this is the circuit that does it, but kind of say, all right, well, this part of the circuit works for this particular distribution of inputs and this particular circuit. So yeah, I do agree that's a possibility, but again, I think the explanation should include that information, and we cannot just say, well, this is the circuit, and that's
Right.
it.
Okay. Yeah. That makes sense.
Okay, does SAEs work? Okay, well, SAE, so I didn't look into sparse autoencoders for this work. The thing with sparse autoencoders is I'm not that familiar with them, but as far as I understand, we're really only looking for the high-level features and not necessarily in how the neural network is using those features, or there's I feel like there's mostly the where part, sorry, or rather the what part, but we don't really know what they correspond to and how they are used in the neural network. So the work doesn't really focus on that. I'm not really sure either what are the metrics used to validate sparse autoencoders, because how do you do evaluation of a sparse autoencoder? I mean, you can check whether your features that you find agree with some initial features of a dataset, but I would kind of argue that in their current state, they don't don't really provide full explanation in which we will say, well, there's this algorithm and it's in this place of a neural network. Okay, we'll come back to this. Counterfactual is similar to different means. Counterfactual really just means that we set the value of some variable to a value that does not appear anywhere in the dataset, or not necessarily, but a value that it wouldn't naturally have. So it's really the idea of, in the terms of medicine, for example, when we're looking at the effect of different treatments or different features. The typical example is, does smoking cause cancer? Correlation is just looking, well, people who smoke are more likely or not to have cancer. Intervention is saying, well, if now I start smoking or now I stop smoking, what are my chances of getting cancer or not in the future? And counterfactual is essentially saying, if I hadn't been smoking, like if 20 years ago I hadn't started smoking, what would be the effect of that intervention on today's data? So it's something that typically in medicine we cannot perform it directly because we don't have the data, but for neural network we can actually go back and change the computation values to values that they did not actually reach in practice. And what about computational redundancy? I also think that, yeah, again, there is definitely redundancy going on, but then you cannot just say that, well, if it's just this tiny part of a neural network that does my task, if there are 3 or 4 other circuits that trigger sometimes. I think if you really say this part of a neural network does my task, it implies that the rest of the network is not doing anything. So if there is redundancy, I mean, it's quite obvious to me that there is redundancy, but that redundancy should be included in your explanation. You should say, well, this part is also active only sometimes, and in this case that is okay.
Maxime, can you hear me?
Yes, I can.
Yeah, sorry for, but in your experiments, you don't consider redundancy, for instance, because it could be that two circuits give the same output, and they like somehow come to a voting or some kind of those things, and you didn't do that, right? Because every circuit is like a unique explanation, right?
Yeah, no, I didn't check for that, and again, I think it's very likely to be the case, but then it still shows that the metric that we have, where we validate a circuit by just checking that the input agrees with the output, that the output agrees on both the circuit and the full network, is not enough. It's really not, I mean, my goal is not to say, well, there's actually 50,000 explanation for every single behavior of every single network. No, it's really just to say, if we have an explanation, the criteria we're using to validate those explanations, they need to be strong enough to ensure, or at least to decrease the risk of finding multiple valid explanations. So here in this case, yeah, the metric we use should be able to account for redundancy and shouldn't validate your explanation if it only includes a small part of a neural network, but actually more of that is involved because of redundancy.
Okay, thank you so much. It was very interesting, your talk.
Thank you.
I know you answered this one, but I still don't quite understand that interpretation search scheme. Like, how do you have like same neuron labeled as both NAND and NOR? I mean,
yeah,
what changes?
So no, that's a good question. That is the one thing that I skipped over, but I do have a slide on that at the end. So essentially, what we do here for this part is, once we have a circuit, what we do is that we start from the input, because the input is, we know there are numbers between 0 and 1, I mean 0 or 1 with some noise, and essentially we check for each input parent, what does the output value end up in. So for example, let's say you know that the output of your network is going to be a 0 or 1, and every time we look at the parents and we try to decompose based on which values of the parents our output is going to be 0 or 1. And so, for example, let's say here our input x, we know that its value is between -0.5 and 0.5 and corresponds to 0, or somewhere around 1 and it corresponds to 1, and then the same for y. And when we plug those values into the network and we look at one particular neuron's activation, essentially we look at where the activations of a neuron land depending on the inputs of a parent, and we get different zones based on whether parent 1 is a 0, parent 2 is a 1, and so on. And sometimes those zones don't overlap, and that's exactly what we're looking for. And so, for example, let's say that here your neural activations they are in this area on the left if x is 0, y is 1, then they're in this area if x is 0, y is 0, and so on. So we get 4 different intervals, and we want to interpret that neuron here as some kind of logic gate of its parents. And well, the natural thing to say is that, right, we look at the activation of this neural network, and if those activations are high, we're going to say that it's a 1, and if they're low, then we're going to say that it's a 0. But the question is, where do we cut off what is a 0 and what is a 1? And essentially, we can just put that cutoff point in different places. So if we just say that, well, the threshold is here, everything that's below that is 0, and everything that's after that is a 1, then we are essentially saying that our neuron here just computes a logic gate that always returns 1. So it's the true gate.
Okay.
If we put the threshold here, we get a different gate, and so on. And we essentially get three possible gates in this case, or 5 if you count the trivial 1 and 0. And if you do that, and then you iterate over each layer and until you reach the output, and you make sure that your output, you also get something that is equivalent to XOR, then you can keep that interpretation, and that's how you get multiple of them, essentially.
Got it. Thanks. Yeah. So basically, like the thresholding is our interpretation, essentially. Like
yes,
how
this is the proxy we're using for interpretation is where do we put the threshold here.
Got it. Thanks.
And it's kind of a lower bound of the actual number of interpretation, because also here we're assuming that one neuron is one logic gate, but you could imagine a logic gate is over several neurons, or that one neuron participates in several logic gates at once. So so it's kind of a lower bound.
Okay.
Coming back to check if there were additional questions. No, nothing in the chat. Okay, if there are no other questions, I think we could end here. Okay, well, thank you very much for the feedback and the questions and your attention in general. Yeah, so it's my first time on this server, but I'll be happy to join the reading group in the future and to see how it works. And yeah, thank you, everyone.
Thank you. Really amazing.
Thank you.
Thanks for the talk.
No problem.
By the way, the recording, like the audio sounds weird, but I think it's mostly okay. Like at some point it broke and I was trying to fix it. And at
Okay.
the end it sounds
Well,
okay, but yeah.
I think my microphone levels are also pretty low in general, so I don't know if that contributed
Yeah,
to it.
no, but no, it was because the virtual machine I used to set up the recordings and all that was dying, and I think just the lag made you sound like weird because it
okay.
was, yeah, but it's okay.
Okay, well, yeah, I guess I'm just going very quickly through the bibliography in case, so it can be in the recording. But I can also just post the slides.
Oh, no, that's okay. You can post the slides if you want on the channel. Yeah.
Yeah, sure, I'll do that.
But yeah.
Okay. Right, so thank you very much. I guess next week it's a different paper, the one from Anthropic.
Yeah, next week we are probably going to do the like the Anthropic post with about the circuit search thing they did. But we already did they have 2 papers on that one, and we already did the biology one where they explain the results. We are going to look at the other one where they explain the methodology, and Gonzalo is probably going to do a presentation or something because he is also working on replicating that in Elixir. But yeah.
Okay, sounds great.
Goodbye.
Thank you all.
Okay, thank you. Goodbye.
Bye-bye.
Uh,